Hello again, it's Mrs. Tremblay, and we're going to finish up 12-2. And today we get to talk about how to approximate square roots. And if you think about the word approximate, it means it's not exact. It's pretty darn close, but it's not exact. You can use perfect squares to help you estimate radicands. Remember that number underneath the radical, that are not perfect squares. For example, if I asked you to find the square root of 52, we know that 52 is not on the perfect square list, right? And we know that because it falls between the square root of 49, or 7, and the square root of 64, which would be 8. And we had kind of talked about before, if the square root of the square root of 49 is too low, and the square root of 64 is too high, there's not a whole number between 7 and 8. So basically that means that the square root of 52 is between 7 and 8. So we can kind of approximate that it's between 7 and 8. That's the approximate value of it. So now I want to know which one is it closer to. And we're going to use a number line to help us figure that out. Even if you can just look at this and know it, I still want you to be familiar with the number lines because the Common Core kind of calls for that. So please make sure you're filling all this stuff out. All right, so the way to use a number line for this, you take a look at what's given. It's the square root of 52, and if you figure out which two perfect roots it's between, that's a great starting point. That actually lets me know where I can kind of start and end my number line here. So I'm going to, at the beginning here, I'm going to put the square root of 49, and at the end, I'm going to put the square root of 64, because I know the square root of 52 is between there. Now, if this was a 1 and this was a 10, and I wanted you to put 7 on there, wouldn't you draw some little tally marks and count up? It's the same thing here. It's okay that it's square root. It doesn't matter. It's fine. We know that this means 7 and this means 8. And if I'm trying to get you the square root of 52, let's count up. And in looking at this, I don't think I want to go all the way from 49 to 64 counting by 1. Because, let's see, if I do that, I'd have to make, it's like 15. From 49 to 64. When I think of the number 15, I think I might want to count by 3s because 15 is divisible by 3, or maybe count by 5s because 15 is divisible by 5. And it looks like we have enough space to count by 3s. And if you're counting by 3s and you're trying to get up to 15, between 49 and 64, which is 15, you'd go 3, 6, 9, 12, and that would be the 15th. So I need to basically make 4 marks in between there. So go 1, 2, 3, 4. Okay, and they don't have to be perfect. Just get as close to perfect as you can. The roots aren't even perfect, right? The square root of 52 is not perfect. Nobody's perfect. Okay, so next I'm going to put the square root of 52 because 49 plus 3 is 52. And wow, that's exactly the one I wanted. I'm going to put a dot right there because that's where the square root of 52 is. I do need to finish off this number line though because we just can't leave it undone. So 52 plus 3 is 55, 55 plus 3 is 58, 58 plus 3 is 61, and yeah, 61 plus 3 is 64. So we can see here that if this is 7 and this is 8, the square root of 52 is much closer to 7. So when I asked you to approximate to the nearest integer, that's what I'm asking you to do next, you can go ahead and write 7. Now, if I actually asked you, okay, well, what do you think the decimal of that would be? How could you figure that one out? If we were in class, I'd make you talk to one another about it. If you're absent, it's hard. You can't really talk to yourself, right? I do all the time. I'm talking to myself right now in my basement. It's really sad life. Not really, I'm just kidding. My kids are being quiet. It's nice. Alright, so in looking at this, I see from here to here, from 7 to 8, I have 1, 2, 3, 4, 5 spaces, right? So if I have 5 spaces and I was trying to decimal this out here, wouldn't each of these be worth 2/10? Like 2, 4, 6, 8, 10? So technically, this would be 7.2, this would be 7.4, 7.6, 7.8, and then we get to our 8. So if I didn't ask you to round to the nearest integer, if I asked you to give me a decimal answer, you would want to end up converting all of these to what their decimal version would be, and it basically just depends on whatever your number scale is. So I could also say about 7.2. And that would be a decimal approximation. Okay, so now I'd like you to try a couple, and it just says estimate to the nearest integer. So we don't have to worry a ton about what the decimal would be. We'll talk a lot more about that in class, but for now I just want you to kind of get which whole number it's closer to. So we have here the square root of 33. The first thing you'd want to figure out is the two perfect roots it's between, because 33 is not a perfect root. So maybe you have your chart out. If you wanted, you could. You don't have to. But basically, when I see this, I think, okay, let's see, with 33, the next lowest one would be 25, square root of 25. And then after that, I have the square root of 36. So the square root of 33 would be between the square root of 25 and 36, because those are the two perfect ones. All right, and 25, again, the square root of that is 5. The square root of 36 is 6. So we know which two whole numbers it's between. We want to figure out which one. So I'm going to make a nice little number scale here. Make a number line for me, please. And I'm going to start off at the square root of 25 over here, which is 5, and the square root of 36, which is 6. Okay, so from 25 to 36, that's 11. So I need 11 marks. I can't really think of anything I'd want to count by if I need to get through 11 marks. So we'll just do it. Let's just count by ones. And if I need 11, this last one would be 11. So that means I need to make 10 marks, kind of equally spaced between here. So we'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And I think this will get kind of crunched up if I put all of them on here. So maybe I'll just put every couple, or maybe I'll just put the square root of 33 on here. If this is 25 and I'm counting by ones, here's 25, 26, 27, 28, 29, 30, 31, 32, and 33. So right here, this would be the square root of 33. And if you're looking at the graph, which integer is it closest to? Yeah, it's much closer to the 6. So I'm going to use these little squiggly equal signs to mean that the square root of 33 is approximately 6. If you wanted to go ahead and figure out your decimal value of that, then you could say, okay, well, from here to here, let's see, this is 1, 2, 3, 4, 5, 6, 7, 8 out of 9, 10, 11. So you could take 8 divided by 11 to get the decimal version. It would be 5 point whatever 8 divided by 11 is. So that would come out to about 5.72 if you were trying to get the decimal version of it, which is closer to 6. All right, next one over, I have a square root of 85. And again, your first step is try to determine which two perfect roots that's between, because it's not a perfect root. So if it's not a perfect root, we want to figure out which two perfect roots it's between. So maybe you have your little list of square roots out in front of you. That could be helpful to you with all this. But when I see 85 in my chart, I think, okay, well, the square root of 64 is 8. The square root of 81 is 9. Okay, that's really close. So I have the square root of 81, which is 9. And then after that would be the square root of 100, which is 10. So once you know which two perfect roots the square root of 85 is between, we can make our number line. All right, now, if I'm trying to get from 81 to 100, like, I don't know about you, but if I start with 81, then I can't count by 5s. But if I start at the square root of 80, I could totally count by 5s, which I think would be a lot easier to do. All right, so let's do that. Let's put the square root of 80 here, and we'll have the square root of 100 here. And if I'm counting by 5s, I would have 85, 90, right? 85, 90, 95, 100. So 85, 90, 95, 100. And you might not, maybe you didn't count by 5s, maybe you counted by 4s, maybe you started at 81 and you counted by 1 and made a whole bunch of little tiny tally marks. You're still going to be able to get to the same answer at the end, so it's fine. Alright, so the square root of 81, that's 9, so I'll put the 10 underneath here, And if I have 80 here, then this would be 1, 2, 3, 4, and 5. So this right here would be our 9. Okay, we're trying to put 85 on here, which, bam, there it is, right there. And which integer is it closest to? It's definitely closer to the 9. So I'm going to write almost equal to the 9. All right, moving along. I have the square root of 115. So the square root of 115, I want the two perfect roots it's between. If you have your chart handy, it'll be really helpful to you. You'll see that the first perfect root would be the square root of 100, which is 10. And then after 10 comes 11, so that means I'm dealing with the square root of 121. All right, so we need to know which one it's closer to. We're going to use our number line to help us out. All right, so with this one, I am going to start with the square root of 100 here, which is 10. And again, do you see how I have the 121? I'd rather count to 120 on my number scale, so I'm going to go 120 right here, and I'll still put this 121, and I know that this would be my 11, would be that next one up from there. And we can, it's not going to be perfect, and that's okay. Alright, so if I want to get from 100 to 120, I again would recommend counting by 5s, except down here where I just put that 11 on there. So if I'm going from 100 to 120, I want 105, 110, 115, 120. 105, 110, 115, 120. So here's my 105, here's my 110, here's my 115, and that's what I want. So here's the 115, and I'm asking which integer it's closest to. When you look at this, it's obviously closer to the 11, right? So I'm going to put my almost equal to and my 11 right there. All right, scooching this over. Now I have this, the opposite of the square root of 7. So here I have a little negative sign. Oh my goodness, it's okay. It just means that it's negative. I want the negative version of it. All right, so when we're trying to figure out what it's closest to, which two integers it's between, when you look at your roots, if I have the square root of 7, actually I'll just show you what I mean here, because I have it handy in front of me. Right here, I have the square root of 4 and I have the square root of 9, right? Wouldn't the square root of 7 fall in between those two? So this is what I'm talking about. When you're trying to determine the square root of 7, you have to figure out which two perfect roots it's between. So I'm going to go ahead and write the opposite of the square root of 4 and the opposite of the square root of 9, which would make this a -3, and a -2. I kind of flipped them. I don't have my little magic whiteout pen, but we know that the square root of 4 is 2 and the square root of 9 is 3. So hopefully you're okay with that. I'm learning to be okay with it. I'm a little type A. It's a problem. Okay, let's graph this thing. Alright, so our lowest one was which one? This is where it gets a little bit tricky, because I'm asking you to put a negative on the number line. When you put negatives on the number line, aren't the lower values to the left? So that means I actually want the opposite of the square root of 9 here, and I want the opposite of the square root of 4 here. Again, this represents -3, this represents -2. On a number line, the lower the value, the farther left that it is, right? And with negatives, the higher the digit, the lower the value. So don't mix those two up. It should be just like this. Okay, and with this one, if I'm only going from 9 to 4, I think just counting by ones would be just fine. Hopefully you agree with me. And I would have the opposite of the square root of 8, opposite of the square root of 7, 6, 5. Oh, I kind of overshot that one, huh? Let's just put the opposite of the square root of 4 here, and we'll pretend this over here never happened. This is why you always write in pencil. If I wrote in pencil here, you wouldn't be able to see it, though. Alright, so hopefully you're okay with this example. There's all kinds of mistakes going on. I'm actually recording this at nighttime instead of in the morning, so I don't have my A game. I didn't have any coffee before this. Alright, so the opposite of the square root of 7 is right here. And then looking at this one, I see that it is 1, 2 away from the -3, and it's 1, 2, 3 away from the -2. So because it's only 2 away from the -3, I'm going to call this almost equal to -3. And again, we could give decimal approximations. That's not going to be our primary focus for today. We will talk about that in class some more, though, I promise. Okay, So in doing that, that will now allow you to compare real numbers. And again, real numbers mean rational or irrational. So I want you to be able to compare the two of them. So the number line again is going to help us do that. So example, I ask you to compare the square root of 5 and 2 3/4. So 2 3/4 isn't too tricky to put on a number line, right? But when we have the square root of 5, I don't know, right? That doesn't jump out at you. It doesn't mean that it's 5. And that's where you'd have to look at the square root of 5 and determine, okay, what 2 is it between? Which two perfect roots? So the square root of 5 is between the square root of 4, which is 2, and it's between the square root of 9, which is 3. And if you looked at your chart, here's 4 and here's 9. The square root of 5 has to fall in between those two. That's how I knew where those were. And again, it'll come with practice. So that doesn't really help us tremendously right now with comparing them. Reason being because 2 3/4 is also between 2 and 3, right? So we're going to put both of these items on the number line, and we'll be able to figure out which one is greater because the values that are farther to the right are greater than those to the left. So for starters, let's see here. I'm going to go ahead and do what we did before, and I'm going to put the square root of 4 here, which is 2. And I'm going to put the square root of 9 here, which is 3. All right? So what we need to do is we need the square root of 5 to be on here as well. And if I'm going from 4 to 9, then we would have 5, 6, 7, 8. So 5, 6, 7, 8. Square root of 5, square root of 6, square root of 7, square root of 8. Okay, so here's the square root of 5. And if I had 2 3/4, 2 3/4, we kind of need to figure out what these are worth as decimals, right? We could fraction it out if we wanted. There's 1, 2, 3, 4, 5. So this right here would be 2 1/5, 2 2/5, 2 3/5, 2 4/5, and then 2 5/5 would of course make 3. The only thing is that this isn't fourths, it's fifths, and I don't think I want to change those into fourths. I'd rather change them into decimals. And 3/4 is one of those that maybe you look at it and you know, oh, that's 75 hundredths. This means 2.75. Or maybe you need to set it up for long division and do 3 divided by 4 to change that. But 2 3/4 is equivalent to 2.75. And when you're dealing with fifths, 1 divided by 5 would be 0.2. 2 divided by 5, 0.4. 3 divided by 5, 0.6. Can you guess what this one would be? Yeah, 2.8. And then we have our 3. So with 2.75, if this is 2.6 and this is 2.8, 2.7 would be right there. 2.75 would be right about there. So here's our 2.75. So if you're determining, hey, which one is greater, the 2 3/4 is greater, because it's farther to the right. So hopefully you get the gist of this. It shouldn't take quite as long once you get the hang of it. But let's try a few more. Okay. It says, which is greater? And it would be nice if it just said that, because then it would kind of let you off the hook, right? But it says to justify your answer. That means I want you to show me proof of your answer. Let me know how you know. So with 4 1/5 and the square root of 23, I want to put those both on the same number line. And then that allows me to compare them pretty easily. 4 1/5 wouldn't be too bad to put on the number line, but the square root of 23 is a little bit more difficult, right? So with the square root of 23, if you're looking at your chart, the square root of 23 would fall between the square root of 16 and the square root of 25, right? Because 17, 18, 19, 20, 21, 22, 23. Yes. So the square root of 16, which is 4, and the square root of 25, which is 5. Well, 4 1/5 also falls between 4 and 5. Crazy, isn't it? All right, let's put this square root of 16, square root of 25 on our number line here. And to get from 16 to 25, let's see here. I think we could count by 17, 18. How many do we need? We need 9. So why don't we count by 3s? And then it would just be 3, 6, 9. Does that sound good? I can't hear you. Sorry. Square root of 19, 16, 17, 18, 19. square root of 21, and then 22, 23, 24. Oh no, that didn't work, did it? Oh, because this should be a 22. All right, there, easy fix. So we've counted by threes, and the square root of 23, if this is 22 and this is 25, 23, 24, 25. So right here is our square root of 23. Now we need to place 4 and 1/5 on here, right? 4 and 1/5. So this is 4, this is 5, and if I'm going 1, 2, 3, wouldn't this be 4 and 1/3? And this would be 4 and 2/3, and then we'd have our 5, right? Okay, so let's see here. I know that this is 4.3 repeating, this is 4.6 repeating, and 4 and 1/5, we just did fifths. 1 divided by 5 is 2, so this will be 4.2. So I'm thinking 4.2 will probably be right around here. So here's 4 and 1/5. Here's the square root of 23. Which one's greater? That would be the square root of 23. So the square root of 23 is greater because it's farther to the right on the number line. Okay, before we do anything on this one, I have the square root of 10. I have the opposite of the square root of 5. So this right here, isn't this going to be positive? And isn't this going to be negative? And when you're dealing with a number line, won't the positives always be greater than the negatives? Yes, so with this one, we don't have to draw all this out. We can just say the square root of 10 is greater, and why? Because a positive will always be greater than a negative. A positive will always be greater than a negative. All right, the next one, oh, they have the same sign. I was hoping it would be a little bit easier. We have the square root of 15. Step 1, let's determine which two roots that's between. Well, I know the square root of 16 is too high, right? And then the next one down, if the square root of 16 is 4, then it would be 3 squared, which is 9. So the square root of 15 is between 3 and 4, so is 3.5. Man, let's put it on the number line. All right, I've got my square root of 9, got my square root of 16, and I think I'm just going to count by ones because that seems like the safest bet for me this late at night. So 10, 11, 12, 13, 14, 15. All right, 10, 11, 12, 13, 14, 15, and there's my 16. Square root of 11, 12, 13, 14, 15. Okay, so the square root of 15 is right there. And 3.5, wouldn't that just be halfway through? This is 3 and this is 4. So I've got 1, 2, 3, 4, 5, 6, 7 lines here. So halfway would be 3.5 lines. Again, from here to here was 7 hops. 1, 2, 3, 4, 5, 6, 7. 3.5 means halfway in between. So half of 7 is 3.5. So 1, 2, 3, and then another halfway. This would be 3.5. So the square root of 15 wins. The square root of 15 is greater. Oh, I forgot to circle the square root of 10 up there. Because it's farther to the right on the number line. Finally, we're done. See ya.